Good morning, everybody. This is Kashyap Saharana, your host for today's conference. I warmly welcome all of you to the second day of 4th International Conference on Life and Chemical Sciences, organized by IM Group of Researchers. Today, we go onward on a journey of collaboration and knowledge sharing, bringing together young and passionate researchers from around the globe. Our platform, after 1 year of dedication, has hosted 3 international conferences, 6 webinars. Now we are driving into book chapters and 19 review articles, with 98 authors reflecting our commitment to excellence. And we contributed to social causes like Flood Relief Fund and Palestine Relief Fund. I would like to express my gratitude to the remarkable individuals who have played pivotal roles in our success. Dr. Fahmida Javeen, the Executive Director of and Patron-in-Chief from Bahauddin Zakriya University, Multan, and Dr. Adnan, our Director from University of Swat, who have been actively involved. I extend my deepest appreciation to the Honorable Professor Dr. Memuna Ghafoor Shahid, who serves as patron and co-patron, as well as our esteemed team members Azazul Islam, Mushtaq Ahmad, Miss Faiza, Dr. Sadia Bano, Miss Aksa Iqbal, Safia Khan, Dr. Sara Junaid, Maham Iqbal, Miss Riaj Iqbal, Atir Naim, and myself as well. Together, we lead this dynamic organization with unwavering dedication. Currently, I am doing PhD in chemistry from East China University of Science and Technology, Shanghai. So, as a doctoral researcher myself, I'm excited to be a part of this vibrant conference. I'm very grateful to all of you for joining us today. We will be shortly starting our conference, so if anyone from your friends is missing, please inform them to join quickly as we are all set for the virtual stage for our dynamic and inspiring conference. So let's start with our session with a few verses of Holy Quran. So I would request Mr. Idris Ahmed to please join for the recitation.
I am audible, him?
Yes, you are audible.
Oh, okay. أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. اقرأ باسم ربك الذي خلق. خلق الإنسان من علق. اقرأ وربك الأكرم الذي علم بالقلم. علم الإنسان ما لم يعلم. In the name of Allah, the most gracious, the most merciful. Read with the name of your Lord who created everything. He created man from a clot of blood. Read, and your Lord is the most gracious, who imparted knowledge by means of the pen. He taught man what he did not know. Sadaqallahul Azim.
Jazakallah Idris. Now we will play national anthem. all what we can do. So we have respected Dr. Ashraf Ali with us as the first speaker of today's conference. He completed PhD in analytical chemistry from Inha University, South Korea in 2018, had been postdoctoral research fellow at Inha University at South Korea till 2020. Currently, he is working as assistant professor in Department of Chemistry at University of Haripur. He has published 43 research articles in well-reputed scientific journals, one patent, and 15 conference papers. He had won several prestigious awards such as Outstanding Research Awards and Dean's Awards for the Best Researcher during PhD. He had received several travel grants, awards, and presented his work at international conferences in USA, Italy, Belgium, Switzerland, Japan, and Singapore. He is working on the synthesis of porous core cell and layer or layer silica and their surface functionalization and chromatography for the separation of various analytes. His other research areas are pesticides analysis in food and water using LCMS and water remediation using low-cost agricultural adsorbent. Sir, you are warmly welcome to our conference and I'm highly thankful for your precious time. You kindly start with your lecture.
Uh, Thank you so much, Kashaf, for such a nice introduction. Can you hear me?
Yes, sir, I can hear you.
Okay, so assalamu alaikum to all the participants and good morning. I will try to share my slides. Can you see the slides?
Yes, sir, we can.
Okay. Thank you so much for to the organizer of the Fourth International Conference on Life and Chemical Sciences and giving me this opportunity to present my topic and some of my research to such a valuable listener. And I hope you will enjoy this lecture and you will learn something from it. The topic of my today's presentation is the development of HPLC and CC columns for highly efficient separation. Um, and as Kashaf have already introduced me, so I don't want to introduce once again myself. And I will directly go to my second slides. And this lecture, I will talk about the different types of stationary phases and HPLC column, and also another kind of column which is mostly used in nano LCR, capillary electrochromatography. So the layout of this presentation is about how we can make different types of stationary phases and how we can pack these columns. Mostly we use the column like C18 and some other columns. We buy these columns from the commercial vendor. But in this presentation, I will tell about how we can make these stationary phases by ourselves and how we can pack this column and how we can design different types of stationary pairs which have specific chemistry for separation, because you know that for the specific in the light separation, the column chemistry and column selection play a very important roles, and most of the researchers have problems in their sample separation and purification, and that is the reason that they mostly don't have knowledge how to select specific column and how to develop the specific method, how to choose suitable mobile phases, and how to develop other parameters such as flow rate and also some mobile phase additive and also the mobile phase VH. So in this presentation I will mostly focus on these things and this research which I have already conducted. So I will share my experience that how we achieve such a high separation efficiency in both HPLC column and also some capillary electrochromatography column. So at the end of this presentation, I hope you will get some knowledge about the column development, because this field is quite new, and there are a lot of work which are continuously carrying out mostly in US and other European country, but in Pakistan we don't have such a setup to pack our own column. Mostly we buy this column from commercial suppliers such as Thermo Fisher Scientific, Waters Corporation, and some other column manufacturing companies. So here The stationary page which we are using in our column, this may be either the column may be either the non-polar stationary phases or it may be the reverse phase. So in non-polar phases and the normal phase chromatography, we use some polar stationary pages like silica particle or some other polar groups like amide etc. attached to silica particle. While in the reverse phase, we mostly use C8 and C18 stationary pages. So the base material is mostly silica. Alumina is also used as a base material, but due to the superior properties of silica particle, we mostly focus mostly use silica particle as a base material and HPLC column. The column may be the gravity column or it may be high pressure liquid chromatography column. So here the column which I am referring as high performance liquid chromatography column. The silica particles, it may be cortical particle, it may be polyporous particle, it may be the non-porous particle, it may be layer and layer particle, or it may be another types of particles which we call ground silica monolith particle. And these type of particles are introduced by my advisor Professor Chong, who was my advisor at Enha University, South Korea. And these particles have not been reported by other laboratories so far. We have successfully prepared this particle, and then we functionalize their surfaces with different ligands and pack our own column and compare the properties of our homemade column with the commercially available column, and properties such as separation efficiency, resolution, and durability, reproducibility, and long time use. These properties were superior to the commercially available column. Uh, you can see the same images of this particle like in core shell particle. We mostly use the solid core particle, and then we develop a porous layer on its top to decrease this diffusion. And you know that in chromatographic theory mostly we are focusing on the relativity of chromatography like in one diameter equation. So decreasing this distance for the inner light to enter inside the particle, whenever we have less distance, then the separation efficiency will be quite high. Second, the same images you can see here. This is the non-porous particle, and on the right side the two images which I have put, these are silica monolith particle. So in core shell particle, it has several advantages, such as it have short analysis time. If you want to analyze your sample and you are carrying out rapid analysis, then you can use the core shell particles column. And have low consumption of mobile phase, that have high separation efficiency, and the size range of core shell particles from 2.7 micrometer. Polyporous particles, so 90% of the columns which are used in HPLC are made up of this polyporous particle, and it have low flow rate, can be used for the analysis, low consumption of mobile bases because the column back pressure is quite low due to the highly porous structure. If we use the non-porous particle, then there will be high column back pressure. And the third one is ground silica monolith particles, which were introduced by our group. This is a unique kind of particles which structure is not totally round, but it have some irregular structure, and it have high separation efficiency, low production cost, and simple preparation method. We prepare this particle by sol gel method, which I will talk about the sol gel method in the next slide. And after packing, there is another advantageous feature like some flow through channel form inside the column, which further reduce the column back pressure and increase the separation efficiency. So how these particles can be prepared? This is the general preparation strategy for making silica monolith particle. We use a silica source that may be any saline like TMOS, tetramethoxy orthosilicate, or we can also use TEOS, tetramethoxysilane, or we can use tetraethoxysilane. There are two names. Sometimes we also call it the tetramethyl orthosilicate. So tetramethyl orthosilicate or tetramethoxysilane is the same compound. We can use as a silica source, and we can use PEG as a surfactant material. Urea is used to produce ammonia, and this will act as a porogen. And the porous structure of this particle will due to the presence of porogen. So for the formation of any porous material, we should use a porogen. And here this correction will be carried out in acidic medium. So acetic acid 0.1 normal is used to produce to acquire that kind of pH. Under ice cold condition, when we mix these substances and then put it um, inside an autoclave to work at 120 degrees C per 24 hour. So the extra water will be decanted, and then after drying these particle we can get silicon on the lead cakes, which you can see in the soft bulk solid cake. And this solid cake is very soft, so after crushing it and by mortar and pestle we can get some powders. And when these powders are calcination is carried out to remove the extra organic material form or some unreacted TMOS or TOS. So calcination are carried out to remove, to burn out all the organics, and we can get the inorganic silicon only particle. And this particle the preparation summary, you can see on this slide that we can control different types of parameters like surface area, pore size, and also the particle size. These are the few parameters which are very important. So controlling the reaction conditions, controlling the temperature, controlling the reaction time, and also optimizing the reagents concentration and the ratio of different reagents such as PG, urea, acetic acid, and multi-step heating, we can control the pore size and particle size. The particle size of the of silica particle, it will depend upon the concentration of silica source, just like TOS or TMOS, any source which you have used. So increasing the quantity of this material will leading to the increase of particle size. Similarly, the pore size can be increased by addition of more porogen, and the surface area is inversely proportional to the pore size. So if you want to prepare particles having high surface area, then the pore size should be small. If you want to prepare silicon particle of higher pore size, particularly for the separation of peptide protein or some higher molecular weight analyte, then the pore size should be higher, more than 300 angstrom. So the particle which we have prepared having a particle size in the range of 250 up to 350 angstrom. And we can also prepare this particle in quite large amount. You can see we have prepared it from 80 to 85 gram per batch. In one batch we can prepare this much particle. And then we can chemically modify this particle. The surface functionalization mean that we can insert different types of group. It may be C8 group, it may be C18 group. For the insertion of C18 group, we will use C18 reagent, which is chlorodimethyl octadecylsilane, or you can use trimethoxy octadecylsilane. And for the C8 stationary phase, we can use the chlorodimethyl octylsilane or the trimethoxy octylsilane as a reagent. And these reagent can be attached easily to the surface of silica particles. Similarly, we can also use different types of reagent. The morphology of silica monolith particles, you can see in the first image show you the 50 micrometer region, so the particles are quite dispersed well. And the second slide shows 20 micrometers. So you can see that these particles are more similar. This homogeneous particle is very important, because if we have a homogeneous particle, then the column packing will be better, and as a result efficiency will be better. If the particles are heterogeneous, then the column packing will not be too much good, and also there will be different path for the analyte movement. So according to the one dimensional equation, then the atom will be high and the band broadening will be too high, and that's why we cannot achieve sharp peaks for separation. So the same images show that the particles are quite well dispersed. This is the particle size distribution. Particle size distribution, you can see that we have d 0.5 mean that at average particle size number base 1.39 and volume base 2.67. Mostly we consider the volume base. So before C18 modification, the particle was about 2.67 micrometer, and after chemical modification, then the particle size little bit increases, because there is the layer of a ligand develop over the surface of particle, and it reached to 3.64. This is the BTBGH analysis, which shows us how much is the pore size of our particle. So the pore size of the particle before and after modification has been shown in this figure. Then you can see that the pore size decreases after chemical modification. The bare silica particle has been shown by the blue line, and after chemical modification it has shown by red line. So The pore size of bare silica particle, here in this batch it is 319 angstrom, and after chemical modification the pore size decreases to 244 angstrom. Similarly, the pore volume and surface area also decreases after chemical modification. Now, column picking, this is a very interesting part of our work because uh, we to develop a material, a particular surface area, particular size, pore size, and particle size, and then we carried out its chemical functionalization with a variety of ligands. And after chemical functionalization, then the next step is how to pick this column. So for picking chromatographic column, first we have these different types of column. As you can see, we have some narrow bore column. Narrow bore columns are the column whose ID is from 1 millimeter or 1.8 millimeter ID. Middle bore column is 1 millimeter ID, and the higher bore column are the larger column. These are 4.8 millimeter ID. So HPLC columns mostly available and three different types or four different types of ID: 1 millimeter ID, 1.8 millimeter ID, 2.1 millimeter ID, and 4.6 millimeter ID. These are the standard IDs of the column. So for packing our column, first we have to we have taken an empty stainless steel tube which have glass inside, so we call it the glass line stainless steel column. And after that we carried out the end fitting of the column. End fitting means to attach some ferrule and some union to the column and putting some pyrit is a porous material which only allow the movement of mobile phase or solvent but prevent the movement of solid particle. And then attached to this packing setup, we have developed this our own packing setup. For the packing solvent, we use methanol, and this is the nitrogen gas which is just used to push this packing solvent across the column. So after preparing the stationary phase and chemically modifying the stationary phase, then we dissolve that stationary phase and methanol to make a slurry, and the slurry has been put to the column which we want to pack. The column is attached here, and after this we used different types of flow rates. Mostly the packing pressure was about 18,000 psi per 30 minutes, and then 12,000 psi per 10 minutes. And after packing the column, whenever the pressure goes down, then the column was detached from this, and the column was checked for the analysis of separation of different types of test analyte. Here you can see the chromatogram. The chromatogram show you that the peaks are quite narrow, and also the resolution is quite better. The first chromatogram show the separation of test analyte like some small compound, phenol, acetophenone, permethyl to nitroaniline, benzene, and toluene. All the pipe analyte has been separated very well, and this column ID is 1 millimeter and the length is 30 centimeter. And second, the column ID is 1 millimeter, but the length has been decreased. So here the separation has been carried out in 10 minutes. If you want to carry it out, if you want to reduce the separation time, so you have to also reduce or minimize the column length. The next one is the preparation of some mixed mold material, because the previous slide show only the C18 column. C18 column is a reverse phase stationary phase, which is used for the analysis of nonpolar analyte. But here, if you want to analyze some kinds of compound which have both nonpolar and polar moiety, then for their separation we use a mixed mode stationary phase. Mixed mode stationary phase is stationary phase which have both nonpolar and polar moiety. So for this purpose, we modify our silica particle with the also the C18 ligand and also another ligand 1,3 trimethoxycyl propylurea. And this methoxy is a good leading group, so it react with the silica silanol group, surface silanol group of silica, and these amide group has been incorporated. And also in addition to amide group, we have also incorporated C18 reagent. So this kind of stationary pairs have both polar and non-polar moiety, and this can be used for the separation of peptides and protein. This is the same pore size distribution of our particles. So the pore size for this batch, the pore size before modification was 298, and after modification it was 204. So here we use two ligand, that is why the decrease is quite higher. And similar is the case in pore volume and surface area reduction. Now, if you look toward this chromatogram, here the mixture of peptide, small peptide has been separated like the tyrosine threonine and serine, and also some angiotensin 1 and isotosine, etc. And the average separation efficiency is 52,500. This per column. This is per column separation efficiency, and the separation efficiency is quite good as compared to the commercially available column. Um, Here we have also tried some proteins which are quite big, so the separation of protein is much more difficult than the separation of small peptides. Here myoglobin and human serum albumin and insulin, and these three proteins are also separated with quite good separation efficiency, and the average separation efficiency is 35,500 per column. Another one we have here now we have tried to prepare polystyrene bonded stationary phase, and polystyrene bonded stationary phase can also be used instead of C18 column, and this is also a reverse phase stationary phase. So polystyrene stationary phase are prepared by raft polymerization, reversible addition, fragmentation, chain transfer polymerization. So this consists on three steps, and first step we have to attach a ligand which contains some halogen moiety. The reagent here was 3-chloropropyl trimethoxysilane. It insert the halogen moiety, and then next and second step we use sodium dithiocarbamate to insert this functionality, and in third step we use the styrene as a monomer, and it lead to produce a polystyrene layer. So this kind of particle C18 usually make a ligand which attach in the palm of hair, but polystyrene it make a complete layer around the silica particle, and this silica particle as a result become just like a core shell particle. So this is the same images of this page, and the particle size distribution and pore size distribution as we have already discussed in previous slides. Here you can see the separation efficiency is much more better than C18 column, and if you look toward the peak shape, these are quite narrow, and the separation efficiency is quite high. So the separation efficiency per column for the right hand side short column, which is about 35,500 per 15 centimeter, and per meter this efficiency is 236 that means that it is more than 200,000. And for the left hand side, the separation efficiency in per meter, it is also more than 200,000. So it means this is quite good separation efficiency, and this such kind of high separation efficiency cannot be achieved even if you use commercially available 18 column or commercially available any column from Waters Corporation or from Thermo Fisher Scientific or from any other company. So our homemade column have quite higher separation efficiency than the commercially available column. Um, Now this was the first part of this presentation, the development of HPLC column, and next page we will talk about the development of CEC column. CEC is capillary electrochromatography, just like capillary electrophoresis. Here two phenomena are involved. The separation is carried out also, due to the interaction of stationary phase, and also due to the movement of ion due to the electrostatic force of attraction. So two phenomena are involved here, and capillary electrochromatography, stationary phase interaction, and the differential partition of analyte and stationary and mobile phase, and also differential migration of these analyte and the presence of electric field. So for the preparation of CC column, we use a narrow capillary column whose ID is about 50 micrometer, quite narrow. And inside this capillary column, we have developed stationary phase, and that's then after developing the stationary phase, then that capillary has been installed in a cassette, and this cassette was incorporated into the CE machine, and then the separation was carried out. So CC have quite higher separation efficiency as compared to HPLC, and CC have another advantage that we can separate very small amount of analyte as compared to HPLC, in which the up to 1 mic. Let's suppose an HPLC, we use the analyte up to 1 microliter per injection, and CEC we will use only 1 nanoliter. So it consume very small amount of our sample. Sometimes if we have forensic samples, or sometimes the sample which are very in small amount, then we prepare CEC for their analysis rather than HPLC. The preparation is same like how we can develop a stationary phase layer inside the column. First we have to wash this silica capillary. After washing the silica capillary, then we use acid or some alkali to further wash and to remove some contaminant inside the capillary. And after washing this capillary, then we will make uh, the reagent, the mixture of reaction, the reaction which we call reaction mixture. And just like here, the reaction mixture and first step attachment of halogen moiety and second step attachment of that sodium diethylcarbamate, which we have already discussed in case of polystyrene preparation. But here we want to insert here polystyrene and also acrylamide. And third step, if you see, there are two different ligands have been incorporated. One is styrene, one is acrylamide, and also acrylic acid. So these reagent, a very thin porous layer has been developed and on the inner surface of capillary. And you can see the same images of capillary, which is 50 micrometer IED, quite narrow capillary. So the same images show that the stationary phase layer has been uniformly developed over the surface, inner surface of capillary. And when that capillary was installed into the cassette and carried out its separation, you will be confused that what is meant by the cassette. So you look here, here on this slide, you can see this is the cassette which we have used, we and which we put our capillary, and then that cassette is introduced into the C machine. So the people who are working on separation, they will know how we can use this cassette. And here you can see on the left hand side of this cassette we have capillary window for the detection. And after making window, then we insert this cassette into the C machine, and one side is going to the column inlet, and another side is the column outlet. On one side, first the mobile page will flow through the capillary, and then after changing that that vial, then the sample vial will be used, and the sample will be injected to the capillary machine. So you can see that quite high separation efficiency has been obtained for these peptides. And the average n value is about, it is quite high. So it is about 1.7 million, and 1.7 million for column n value has was not been reported, and still it has not been reported by other groups. So this is quite remarkable work, and quite high separation efficiency has been obtained. These are the mobile phase condition that 50 millimolar ammonium format pH 6.5 sample injection was at 2.20 kilovolt per 15 second, and the potential was 20 kilovolt. The current was 15 microampere. So this was the elution condition. Similarly, this electro program show the separation of different types of peptides, peptides mixture, and it have been separated in LC mode. There are two types of mode in CC machine. One mode is called CE mode, and another one is called LC mode. So LC mode is pressure mode. It is just like nano LC, and this CE mode, this is like electrostatic mode. So in electrostatic mode, usually separation efficiency is quite higher, while in the under pressure mode or LC mode, the efficiency is not that much high, but still we have done quite good separation efficiency under LC mode. Separation of large peptides are like angiotensin 1, isotretinoin, and radakirin. These three peptides were also separated with quite high separation efficiency. And here we have also separated the tryptic digest of cytochrome C protein. Sometime if you want to study the structure of protein in detail, we carried out its digestion. So the tryptic digest means trypsin is used for the digestion of this cytochrome C protein, and this was being digested using specific amount of tyrosine. And after digestion, we injected that sample into CC machine, and you can see there are different types of peaks, which indicate that there are so many peptides have been separated with quite good shape and quite good separation efficiency. So this column can also be used for the triply digest of different protein. Main advantages of OTCC column. Open tubular CC column have high efficiency, long lifetime, because this column was used for more than 2 or 3 months, and the drop in efficiency was quite low. Separation of various types of analyte like peptides, small hydrocarbons, and it may also be used different types of compound, but we have not tried so far. This is reproducible. We have prepared so many capillary, so this process was reproducible, and the resolution is also quite good. The distance between the peaks is quite high, and this can be used under both CE and LC mode. And in conclusion, you can see that step by step we have carried out our work. The first 13 bonded sub 2 micrometer silica particle, the N value was 153,100,000, which has been published in Journal of Chromatography A. Mixed mode stationary phase, this has been also been published in Journal of Separation Science. The polystyrene has been also published in Journal of Chromatography A, and this paper has been selected for the cover image of Journal of Separation Science. So this is all about the work which we have have done so far. But in Pakistan, unfortunately, we don't have the packing setup in our university, so far we have not tried that kind of work here. And thank you so much for your time.
I want to invite Dr. Adnan, who is director of IM Group of Researchers and always being a great sport for us, for his conclusive remarks.
Assalamu alaikum, dear valued guests, participants, and esteemed team. Is the fourth International Conference on Life and Chemical Sciences with the theme From Lab to Life, Emerging Trends in Biological and Chemical Sciences come to an end. I want to express my sincere gratitude and pride for the success of this event. On behalf of the organizing committee, I want to thank our guest speakers, participants, and especially the dedicated team that worked hard to make this conference happen. Our goal focused on providing valuable education and raising awareness through research has come to life through the lively discussion and knowledge sharing during these enlightening days. Organized by the IM group of researchers, this conference provided a common ground for the students, researchers, scientists, and professors in life sciences and chemical sciences to share insights, experiences, and the latest advancement in their fields. The objective we set for this conference were not just met but surpassed thanks to active involvement of everyone present. We successfully encouraged collaboration between experts in biological sciences and chemistry, opening doors to innovative solutions for global challenges, discussions on healthcare, drug discovery, sustainable practices, and the exploration of chemistry, of nature, and biomolecular sciences have undoubtedly advanced scientific understanding, paving the way for future breakthroughs. I want to express my appreciation for the commitment shown by participants in promoting ethical chemical research, environmental awareness, and safety measures. This conference has not only been a platform for intellectual exchange, but also a catalyst for building a community of responsible researchers dedicated to making positive impact on society. Uh, Special thanks to our distinguished guest speakers whose expertise enriched the conference and to every participant who actively contributed to to the discussion. My gratitude also goes to the organizing team whose careful planning and ensure the smooth flow of events. I am confident that the knowledge shared and connection made during this conference will go beyond these walls and make a lasting impact on the laboratories, classrooms, and research institutions represented here. As we part ways, let's carry forward the spirit of collaboration, innovation, and ethical responsibility that defined the fourth International Conference on Life in Chemical Sciences. Thank you all for your unwavering support, and I look forward to future endeavors that continue to push the boundaries of scientific exploration and social impact. Thank you all.